All right, so we talk about multiplexing and demultiplexing. Now we should talk about the two protocols we have, UDP and TCP. UDP is a lot simpler than TCP, so we start with UDP, which is connectionless transport. All right, that is generally referred to as no-frills bare bones internet transport protocol. Best effort service, UDP segments may be lost or delivered out of order to application. So by out of order, this means that we will divide the packets into smaller segments and you might receive it in different orders. That is the idea. Okay. Connectionless, no handshaking between UDP sender and receiver. So this means that before saying hello, you start talking, okay? Some people prefer that. Each UDP segment handled independently of others. So question that now arises, if TCP is, provides more properties like reliable data transfer, flow control, and so on, then why do we use UDP, right? Why do we need it anyway? Here are some good things. No connection establishment, like the three-way handshake in the TCP. So such a connection establishment actually creates RTT, right? So you lose some time. So for speed, UDP is faster. Simple, no connection state and at sender and receiver. This is important. We will see that at TCP, both parties will try to, keep the state of this connection. So it will cause to use, more resources. Small header size, due to, you're only storing the ports, but in the TCP, you will be storing IPs and so on. No congestion control. UDP can blast away as fast as desired, can function in the face of congestion. These are the reasons you might need a UDP. And as already mentioned, we said that DNS uses UDP, but there are other applications that use it, like SNMP, HTTP3, which we see at the end a little bit about QUIC protocol. Also, streaming multimedia apps, which can tolerate a small amount of data loss, actually prefers streaming multimedia apps using, UDP. But if reliable transfer needed over UDP, you can add needed reliability at the application layer. This is what QUIC protocol does at HTTP3. And also you can add congestion control at the application layer. Here you take the burden from the network and transport layers, but put it at the application layer. So this is kind of a choice. But again, at HTTP3, if you use UDP, like Google does in Chrome browsers or YouTube application, Google, this is what they do actually. They use UDP, but provide these properties at the application layer. Okay, so UDP is really old. As you can see from the RFC, it dates back to 1980. And some of these protocols are really old, where there are no PCs or workstations at all, no internet at all. Okay, so let's look at an example for the transport layer actions. Here we have SNMP server and client. UDP sender actions are as follows. It is passed as an application layer message to transport layer. Now you have UDP header. This creates a UDP segment. You pass it to the IP, transfer to the links between these hosts. The client receives it. The actions are as follows. It moves it from the IP to, transport layer. There's a checksum at the header, which actually is used for detecting errors. Extracts application layer message. If there are no errors, then demultiplexes it via the socket. So this is how UDP works. So a UDP segment header looks like this. So the 16-bit for source port number, 16-bit for destination port number. So your port can be something between 0 to 2 to the 16 minus 1. So you have the length. Length is the actually reported here as bytes, and it is the length of the whole thing. Checksum actually adds all of this data in 16 bits and at the end obtains a 16-bit value. So there is an addition, actually modular addition here. There addition, it is not an XOR operation, it is addition modulo 2 to the 16. Okay. So we already talked about it. Yes, length in bytes of UDP segment, including header. This is the data you are sending. Okay. Also receiving. Yeah. Let's look at the UDP checksum. The aim is to detect errors. So sometimes there may be flip bits during the transmission. Okay. So here actually, maybe we should stop at this point and explain that this kind of errors can happen at any place. Okay. For instance, maybe there's a device malfunction, so they're actually flipping bits. This can be at the router level or at your computer and so on. So some flips may be bits. If it is due to a hardware error, we call it a hard error at the end. But if it is like for a different reason, for instance, you are keeping data, for instance, routers may keep the data in the memory, and some of the bits might change at the memory again due to some actually physical conditions, okay? And we call them soft errors, and it can happen. So idea is as follows. So for instance, that you transmitted two numbers. Here, as an example, you have 5 and 6. If you add them, the summation is 11. So this is your actual checksum. So during the transmission, assume that this 5 is reported as 4. So the person receives 4 and 6. So they add these two values, right? But it doesn't match with 11. So you detect the error here. Okay. So actually, at this point, we again need to stop and talk about actually this area is just a small part of coding theory. In coding theory, we have very nice codes. I mean, depending on the situation or the medium you are using, we have many nice codes which actually can detect many bit errors, and even they can correct most of them. So we have very nice coding theory results, which we use in every communication, even when you are communicating with Mars. Okay, you will be sending data with this kind of coding theory. Okay, yeah. So let's look at how it works in the internet checksum. So sender treat contents of UDP segment, including UDP header fields and IP addresses, as sequence of 16-bit integers. Checksum addition once complement sum of segment content. This means that you add all of these 16-bit values, then complement the result. Complement means that instead of 0 you write 1, instead of 1 you write 0. Checksum value put into the UDP checksum field at the end. Receiver compute checksum of received segment. Check if computed checksum equals to checksum field value. Not equal, error detected. Equal, no error detected, but maybe error nonetheless, right? Because this is not actually, I mean, you can detect errors up to some bit errors, right? You cannot detect everything, actually. Maybe everything is flipped, but it still matches with the checksum. That is the idea. All right, here's an example. Assume that we have two 16-bit integers. So one of this and the other one is this. So we add them. So as I mentioned, this is not an XOR operation. For instance, when you add 1 to 1, it becomes 2, but we are adding, in modulo 2, right? So it is 0, but you have the carry bit here. In the XOR, you don't have the carry bit. In modular addition, you have the carry bit. So you add these values, but sometimes by chance, you might have an extra carry bit here, right? But you cannot store this value because you have 16-bit variables, right? In this kind of scenarios, if you just get rid of this value, this means that you cannot detect errors at this layer, right? Sometimes. So for this reason, this value actually added to the beginning. So what you do is, as well as you are adding 1 here, so it becomes 0. There's a carry bit, it becomes 0. Carry bit now moved to here. So this is how you do the checksum. So as the note says, when adding numbers, a carry out from the most significant bit needs to be added to the results. Okay. So your checksum is now just a complement of this value. Okay. So instead of zeros, you write ones and so on. So here's an example what can go wrong. So assume that these 2 bits are somewhat swapped. Actually, there are 2-bit error. One is actually somehow replaced with 0, and this 0 is replaced with 1, right? Actually, normally we can detect it, but assume that the same thing happened here. So the summation will be the same. Actually, there are 4-bit errors here, but your checksum cannot detect it. That is the idea. But in coding theory, again, you don't have to do everything like this, but this is a very fast way because you're just adding 16-bit values. So in coding theories, we actually generally have 2 parameters, let's say n and m. This means that you can detect up to m bits errors, and you can correct up to m bit errors. Here, there are no correction. We are only detecting it, but there are very nice codes that you can, detect and correct many bits. So here, even though numbers have changed, bit flips, no change in the checksum. Again, you cannot detect it. Summary is as follows. This is no-frills protocol, meaning segments may be lost, delivered out of order. This is just the best of our service. Send and hope for the best. Okay. UDP has its pluses, no setup handshaking needed, so you have speed from here. Can function when network service is compromised. Helps with reliability using the checksum. You can build additional functionality on top of UDP and application layer, for example, in HTTP 3. Okay.